Hi everyone, welcome back. Today we're going to be discussing volume by cylindrical shells. Now in the previous video, what we were looking at is taking this region that was bounded by some given functions, and we were rotating that region about a certain axis. Once we were able to extract the visual sketch or the visualization of that region being rotated about a certain axis, then what we were using was either the disk or the washer method to find what was this particular volume. And that, in other words, was known as your cross-sectional volume, because you look at a cross-section, you determine within that cross-section what is the volume of each individual slice, in other words, each individual cross-section, and in turn you will then find the volume of the overall figure once you go through the whole integration process. Now, for that process, we actually needed that each cross-section had to be perpendicular to the axis of rotation. Now, that will then bring about this topic that will become a little bit more cumbersome if we say to take this function, which is y is equal to 4x minus x squared, and that it's going to be bounded by the x-axis, or sorry, by the x-axis. And so what we're going to have here, or you know what, this is y is equal to 0, my apologies. That's y is equal to 0. And so if we're taking this region that's bounded by 4x minus x squared and y is equal to 0, in other words, that x-axis, and we're going to rotate this about the y-axis, then what's going to happen here is we're going to get a region or a volume that looks like this. It has a very, very similar shape to a bundt cake. All right, if you haven't seen bundt cakes, you can go ahead and Google bundt cake and you'll be able to see what that is. But at this point in time, that's what we're looking at. And to take cross sections that are going to be perpendicular to the axis of rotation here, then the radius that we're going to be looking at for those cross sections is always going to be the same function. In other words, 4x minus x squared. Which again makes us run into that one issue to say that if we wanted to do this using the disk or the washer method, this would then be very, very difficult because we would have to split the function into two separate equations and then use both of them to find this volume. We want to stay away from that. Herein lies the cylindrical shell method. The cylindrical shell method then says, well, you know what, let's do the exact same thing. Let's take the region that we have, let's rotate that about the y-axis, and instead of getting cross sections, how about we build a cylindrical shell? Hence the name cylindrical shells. And this is what we want to focus on here, is building this cylindrical shell. Now, I have drawn three figures for you on the screen. The first figure on the left is the region that's bounded by 4x minus x squared, y is equal to 0. So that's the region bounded by the parabola and the x-axis. The next picture in the middle is the picture that you would get when you rotate that region about the y-axis. And the last picture that I have here on the screen on the right is the same picture as the middle. However, we now have a cylindrical shell that we want to then analyze. And so in order to extend into this analysis, what we're going to do is we're going to say that we're going to pick a sample point anywhere that we want within our region. Now, if we pick a sample point, call this x star sub I, then naturally we know that there will be some interval that's going to bound this sample point, and we'll call that interval x sub I minus 1, comma, x sub I. And what we want to do, what we're interested in doing then, is to now create this rectangular height that will have a height of f of x star sub I. And that's what we want. Because now, when we create this rectangular height, or this rectangular strip, and we rotate that rectangular strip with that area, then we're going to be creating a volume for that singular rectangular strip. That volume is then going to be modeled by this cylindrical shell. And again, that's what we want to focus on. So let's extract that cylindrical shell, and let's start decomposing that cylindrical shell as much as we can to see what we can then establish. All right, so I'm going to pull off this cylindrical shell down here. And we'll observe it here. Whoops. All right, there we are. Let's bring this downward. So here's your cylindrical shell. There we are. Now, in looking at this cylindrical shell, again, we're interested in finding the volume. So that's going to be our overall goal, is to try to establish some volume here. So I'm going to say the volume for the cylindrical shell. Alright, so here goes the volume for this cylindrical shell. So I'm going to have the volume, and I'm just going to label this as volume for CS, which is a cylindrical shell. And we're going to see here that this volume for the cylindrical shell is actually made up of two different volumes. The first outer circle, this main outer circle, is creating a volume that has a certain height. All right, so we have a certain height h, and it's creating a certain volume. So what we're going to do is we're going to take the volume of the outer figure, so volume of the outer minus the volume of the inner cylinder. So in other words, we're taking this volume of this firm cylinder, and then we're going to punch a hole in it. In other words, we're going to remove the volume of the inner figure. Okay, that means that we have two different radii. And that's perfect because we do. So in order to identify the two different radii that we have, we're then going to identify radii 1 and radii 2. So that's what I want to go into at this point in time. So let's see if we can then identify those two different radii. So I'm going to have radius 1. Okay, so this is going to be r sub 1. That's radius 1. Radius 2 is going to be the outermost radius here. All right, so that's radius 2. So again, radius 1 goes to the inner, radius 2 goes to the outer. And therefore, when we want to create this volume of that cylindrical shell, then the volume of the outer figure is going to be pi r squared, but the outer figure has a radius of r2, and we're going to square that, multiplied by the height of that cylinder, minus the volume of the inner figure, or of that inner circle. So the volume of that inner cylinder is going to be pi r sub 1 squared multiplied by h. And this is because the volume of any right circular cylinder is going to be pi r squared multiplied by its height. So that's a volume always. And now that I have this, I could then see that pi and h, so pi and the height, are always going to be the same. So I'm going to factor that, keeping these two exactly the same. so pi and h. And then what we have is radius 2 squared minus radius 1 squared. But that in itself is a difference of squares. So since it's a difference of squares, we can factor that for this to be r2 minus r1 times r2 plus r1. Alright, so that's looking pretty okay so far. Now let's draw these radii where they're going to be at. So the radii that we're measuring, radii 1, is going to be here. That's radii 1. Radii 2 is going to be that outer radius. There we are. So that's radii 2. Oops, sorry. Looks like it's a point, but it's actually the measurement. There we are. So again, two different radii. And what we're doing when we're looking at them here is we're looking at this particular region here. This is R1, and then R2 is going to measure the outer. There we are, just to get a frame of reference into what these radii are. Now, what's really nice about this is that this particular formula looks very, very familiar. Now, why does it look familiar to us? Well, it looks familiar because what I'm going to do at this point in time is I'm going to introduce a half, and I'm also going to introduce a 2. So 2 times a half is just 1. So I'm going to introduce that 2. There we are. But I can't just multiply by 2 into this formula. I need to also divide by 2. Alright, so I'm going to divide by 2, and I'm going to divide by 2 on this very last term. And the reason I'm going to divide by 2 on that very last term, not just because I introduced that 2, but more specifically because R1 plus R2, that's just radii 1 plus radii 2 divided by 2. In other words, that is the midpoint of the radii. So this is the midpoint of that radii, that sample point that we chose. So if it's if it's the midpoint between radii 1 and radii 2, then that's just going to be the midpoint of that interval that we're looking at. So I'm just going to say here r bar. That's going to stand for the midpoint. But radii 1 and radii 2, those are just x coordinates, which means that we can represent this particular equation in terms of 2 pi times the height multiplied by r1 minus r2. That's just going to be some x value, we'll call it x2 minus x1, multiplied by the midpoint between those two values. That's going to be x bar. But now, if we're taking the interval and if we're subdividing the interval into n subintervals, well, that just means that we're going to go through that process then. Well, what does that process then entail? That's going to entail that x2 minus x1, that's going to be your delta x. Now, that's really nice because, again, we're just getting this particular values, and we're just saying, hey, we're going to find the distance between these two values. Well, that's just going to be delta x. So this now turns into something real nice. 2 pi times h multiplied by x bar multiplied by delta x. And this is going to be the volume for that cylindrical shell. But if we're trying to find the motivating question, or if we're trying to solve for that motivating question that says find the volume of the solid, we don't just want to find the volume for this cylindrical shell. What we want to do is we want to add all of these shells that we will then be investigating, and all of those shells are going to go from the x value of 0 all the way to the x value of 4. So what this then turns into, finding the volume of the figure of the, let's say, volume of the solid Now that we have this that we found, if we take the volume of the solid, then the volume of the solid is going to be made by taking a summation of all of those cylindrical shells that we're finding. And this is going to be 2 pi, we'll say x bar, 2 pi x bar, and again that's going to be the midpoint, multiplied by the height, multiplied by delta x. So let's go through and identify the height really quickly, because that's one thing that's kind of bugging me here. The height is then determined by the input of x sub I star, which means that the height of each individual shell, the height h, is going to be the function value itself. So, and notice, if it's a sample point, well, that's just going to be the average for that interval. So we can rewrite this as the summation of I beginning at 1 for 2 pi times x bar. The height is now the function evaluated at the midpoint multiplied by delta x. But again, we don't want an approximation for the volume of that solid. We want the actual volume, which means we're going to have to subdivide this interval infinitely. In order to do that, we need a limit. We're going to take n going to infinity. And again, we're going to subdivide here. And now we have the summation, I beginning at 1, stopping at n, for 2 pi times x bar times f of x bar multiplied by delta x. But this is the Riemann sum that we're looking at, and it's a Riemann sum where we've partitioned or we've subdivided the interval from 0 to 4 that includes this function, which means that we can then represent this as a definite integral. We're going to say from the values that we were looking at from a to b, and this is going to be for 2 pi x bar, that's just the sample point, which means it's just going to be some x value multiplied by f of x multiplied by dx. And therefore, this is the volume that we're looking at, and this is going to be the volume that we're going to be able to find for this solid when we rotate this region about the y-axis. Now, one thing that you're going to notice here is that the cylindrical shell is going to be parallel to the axis of rotation. So the height of the cylindrical shell needs to be parallel to the axis of rotation. And that's one thing that we have to be always very aware of. The height for the cylindrical shell is always parallel to the axis of rotation. Now again, this now allows us to work in two different ways. Number one, we can work with the shell method to find a volume of the solid that's being rotated about an axis, as long as the cylindrical shells that we observe are then parallel to the axis of rotation. The other method is the disk/the washer method, or the cross-sectional method. The cross-sectional method says that each cross-section needs to be perpendicular to the axis of rotation. So again, two different methods that involve finding the volume. So there are, again, the pros and the cons, but sometimes cylindrical shells works better than the disk or the washer method, and sometimes the cross-sectional method works better than cylindrical shells. It's all on how we look at the figure and how we want to work with that object. So let's go ahead and let's write up what we're doing here. We'll go ahead and we'll get a good definition. That way we can that way we can keep working with the method of cylindrical shells. All right, so here's this definition that we're using for the volume of the region that is being rotated about a certain axis. We're going to say that the volume of a solid that's going to be obtained by rotating about the y-axis, the region underneath the curve y is equal to f of x from a to b, is the integral from a to b for 2 pi x multiplied by f of x dx, where x is bounded between a and b. Now, there are a few things that I want to elaborate on here. All right, so here are the things that I want to elaborate on. The first thing is going to be that your height is going to be your function value. All right, this is going to be a certain f of x. The shell thickness, so the thickness for this shell is going to be delta x. All right, that's the thickness for the shell. And then we're also going to have your circumference. The circumference is just the area, or sorry, not the area, the region for that sample point that's making the circular top. So again, we have a circumference that we're looking for as well. And the reason we look for the circumference as well is because using this definition, then the volume of cylindrical shells breaks down into this piece. We have a circumference, we have a height, and we also have a shell thickness. So we have these 3 different pieces. Now, typically we don't look for that last piece because the shell thickness is just always going to be that dx. But we do look for what is the circumference and what is the height for this shell. The circumference is, once again, based upon the radius that we need to look at for this shell. So this can be represented in different ways. We can represent volume of cylindrical shells by identifying a radius and multiplying that by the shell thickness, or sorry, by multiplying by the height. But in that sense, you still need to multiply by 2 pi because you're making one full rotation. So there are different ways to represent this, and there are different ways to interpret this. However, I want to choose to look at this as what is the circumference and what is the height. The shell thickness, it's automatically going to be dx. Or if we choose dy, then that means we're integrating with respect to y, and we can keep going. So now that we have this set, let's go through and let's try an example. All right, so here's a question that we're looking at. It says, use a method of cylindrical shells to find the volume generated by rotating the region bounded by y is equal to x cubed, y is equal to 0, x is equal to 1, and x is equal to 2 about the y-axis. So again, we're taking the region, and we're going to be rotating that region about the y-axis, and the region is on the left-hand side here. I have y is equal to x cubed, x is equal to 1, x is equal to 2, and y is equal to 0. The region that's bounded by those curves is this area in blue. Now, rotating that region about the y-axis, let's see what that's going to get me. All right, so we know we're going to be at 2 and all the way up at 8. So I'm going to get that going for us. There we are. All right, this is going to make a big circle because, again, it's going to be giving that rotation. There we are. The bottom part as well. There we are. Now the inside function goes up all the way to 1. So what I'm going to do really quickly is I'm going to draw that inside function as well. All right, so at 1, you're at 1. That inside function is then creating a smaller cylinder inside of it. Oops. I went out to 1, but I didn't go out to 1 here. There we go. So it's creating a smaller cylinder here. There we are. And then this function comes straight down. There we go, as such. There we are. So this is that figure that we're looking at right in here. And since we're looking at this figure, again, they're telling us that this is being rotated about the y-axis. So I'm going to use a method of cylindrical shells. Again, the height for a cylindrical shell needs to be the height that is going to be parallel to the axis of rotation. Therefore, when I choose any sample point, choosing that sample point will then create a height for this shell. So the height is going to be the function that is determined by y is equal to x cubed. There we are. This sample point is then located in some interval between 1 and 2. So this is just going to be x. And the reason I need this is because this is going to tell me what my radius is for this given shell. So let's go ahead and let's draw that in here. All right, so I'm going to be grabbing some shell. There we are. All right, there we are. So we found the height for the shell, and we also found its radius. Okay, so that's looking really good then. Then my volume for this figure is then I want to for the volume to find it for this figure using the method of cylindrical shells, you're going to go to the region that you started with that is bounded. That region is bounded between the x value of 1 and the x value of 2. Then we need the circumference of the shell. The circumference is given by 2 pi times x. X is the sample point that's given inside of that interval. So there's my radius. All right, so there's my r value, and again, I can denote that r value. Let's denote it here, that this process right down here will find that r value. Radius, r. In other words, that's just your sample point, x. Now we need the height. The height of the figure, as we found, was just x cubed. And therefore, all we need is the shell thickness, but that's just going to be accounted for with that dx. So again, we have the circumference using the radius of that shell that we're going to be producing, multiplied by the height as well. So all we have to do then is integrate. 2 pi is a constant, which means 2 pi can factor, and we have 2 pi times the integral from 1 to 2, and this is going to be for x to the 4th dx. When we integrate this, this will be 1/5 x to the 4th, evaluated from 1 to 2. 1/5 is a constant. I'm going to factor that out, so we get 2 pi divided by 5, which means I can just evaluate x to the 4th from 1 to 2. Two to the 4th minus 2 to the power of 1. Now, 2 to the power of 4, that's going to be 16. So 16 minus 1, that's going to then be 15. And just making... Oh, I'm sorry. I meant to the 5th. Wow. Cheese and crackers. My apologies here. Let's just erase this. This is x to the power of 5. X to the power of 5. And then this is 2 to the power of 5 minus 2 to the power of... 1 to the power of 5. There we are. So 2 to the power of 5 gets us 32, but 32 minus 1 gets us 31, which means this is 2 pi divided by 5 multiplied by 31. And then 31 times 2 should get us 62. So the answer here is going to be 62 pi divided by 5. And since this is a volume, this is going to be some cubic units. And this is the method of that cylindrical shell. And again, we always want to focus on getting the picture, so getting that quick sketch for the region, then rotating the region so that we can identify what the figure is. Once we identify the region that is made by that rotation, we can then go through and identify what is the height of the cylindrical shell, what is the radius of the cylindrical shell, and then can we integrate to find the values that we need. Perfect. So let's see if we can do some more examples. All right, so here's a second question that we're working on that says, use the method of cylindrical shells to find the volume generated by rotating the region bounded by y is equal to the square root of x is equal to 0, and y is equal to 2 about the x-axis. So again, what we have here is the region where we have y is equal to x squared, x is equal to 0, y is equal to 2. And I believe I said y is equal to x squared, and I meant y is equal to the square root of x. That region is this area that's shaded here in blue, and we're going to rotate this region about the x-axis. And so in order to do that, we're then going to start talking about how we're going to find the volume for this cylindrical shell. So let's go ahead and let's start making that rotation for this figure. So again, what I'm doing here is I'm just drawing this picture so I can denote that rotation that's going to take place. Alright, so we have our y and our x-axis. There we are. So what I'm going to do again is I'm going to look at my points where I'm going to be rotating this function about the x-axis. And so knowing that my points are still going to be at 2 and negative 2 for this y component, also if x is 4, then y is going to be 2. So x is 4, y is negative 2. There we are. Let's get these going. This is going to be the outer part of that region. All right, we're going to make a rotation here. the inside of this region is then rotating, but that rotation is modeled by that square root function. So it looks like we're creating this parabola right inside, and it's going to have an open figure for that parabola. So it's looking pretty cool in here for this region, and again, we got to find the volume that's then being generated by this region. So again, it has an opening, and we're not trying to find the opening of this parabola. We're trying to find the volume that's generated outside of the opening for that parabola that's going to be bounded by that given region. So when we want to use the method of cylindrical shells, remember, your cylindrical shell needs to have a height that is going to be parallel to the axis of rotation. Therefore, if the axis of rotation is the x-axis, then your cylindrical shell will have a height that is going to be parallel to that axis of rotation. Alright, so there's my height. So I'm going to have some height h. There we go, I'm going to have some height. But that means that the sample point that we chose, the sample point is on my y-axis. So the sample point here, that's just going to be y, and that is going to be on some interval between 0 and 2. In other words, that is the radius that we're looking at for this shell. So this is the radius. The radius is just equal to the y value here. Just r is equal to y. So again, we have some height, and then determining the radius of that shell, well, the radius is just r is equal to y. Again, here's my cylindrical shell. There we are. So again, we got the radius, we got the height. Now let's interpret what this is going to be in terms of its volume. The volume of the figure is going to be 2 pi multiplied by the radius. The radius, we said it's just some y value inside of the interval from 1 to 2. Therefore, we get 2 pi y, which means that we are going to be integrating with respect to y. Therefore, the region that is then bounded, we're going to bound that region, and we're going to observe what y values are bounding that region. The y values bound that region from 0 to 2. All I need now is the height of this cylindrical shell. Well, the height of this cylindrical shell, doesn't matter where we pick that cylindrical shell. This cylindrical shell could have been down here. That height is still going to be x is equal to 0 from the left all the way to the right. It's going to be y is equal to the square root of x. However, we're not looking for y is equal to something here, or actually we are looking for y is equal to something here, and y is equal to the square root of x. Therefore, the height, my height value here, is just going to be the square root of x. But notice that height is in terms of x, but r is in terms of y. In other words, we need to integrate with respect to y. The function y is equal to the square root of x isn't in that form that we need it to be. So what we're going to do is we're going to manipulate this algebraically. If I square both sides, I then get that y squared is equal to x. In doing so, I could then see that any value that I choose for my x value will correspond to my function y squared. And this is not a regular function. This is a function in terms of the y variable. So in other words, I'm integrating with respect to y, which means I need to convert y is equal to square root of x into a function in terms of y, and this is how we do it. We get x is equal to y squared. Therefore, our height is just y squared. Therefore, when we're integrating, we have 2 pi y, that's going to account for the circumference because y is the radius. Then the function height is just going to be y squared, and this is going to be with respect to dy. 2 pi is a constant. Which means we integrate y cubed with respect to dy. Now, doing this will get us 1/4 y to the power of 4, evaluated from 0 to 2. 1/4 is a constant. I'm going to factor that out, so 1/4 multiplied by 2 pi, that's going to get us pi halves. And then we're going to evaluate y to the 4th from 0 to 2. Well, evaluating 0 into y to the 4th would just naturally get us 0. So all we really need to do is evaluate 2 to the power of 4. But 2 to the power of 4 is going to be divided by 2, which means we just take away 1 from the exponent, which is 2 to the power of 3, and that's going to be multiplying pi, which means 2 to the power of 3 times pi is 8 pi. And this is, again, cubic units. So there we are. The volume for this figure that we generated by rotating it about the x-axis has a volume of 8 pi cubic units. Again, we must always analyze what is the region, what is the solid made by rotating that region about a certain axis, and then we can go through and identify what is the radius of the shell, what is the height of the shell, and then what are we integrating with respect to. That way we can find the thickness of the shell. Awesome, so everything's looking good so far. Let's keep upping the ante. So let's go a little bit more further and let's find a different example that will then take this to the next level. Alright, so here's the next question that says, use a method of cylindrical shells to find the volume generated by rotating the region bounded by y is equal to the square root of x and x is equal to 2y about the line x is equal to 5. So on the left side here below this question, I went ahead and I sketched this area. I sketched the square root of x, so y is equal to the square root of x, that was my green function, and I sketched x is equal to 2y, which is the orange function. They intersect at 0, 0 and at 4, 2. Those are the coordinates. The area that's made between them has the function y is equal to the square root of x up top, and it has that area bounded below by x is equal to 2y. And we want to rotate this region about x is equal to 5. Now, I haven't rotated the region just yet, and again, because I want to show that that region is going to be rotated along x is equal to 5. So coming through here, where we have x is equal to 5, I'm going to have my axis of rotation. So this is my axis of rotation where I have x is equal to 5. There we are. So we're going to be spinning around that axis. Now, to graph this, I'm going to graph my outside function first. That's going to be at 0, 0. It's also going to be at 1, 1, and it's also going to be at 4, 2. There we are. Alright, so there's my first function. Now I'm going to try to reflect this across that axis of rotation, x is equal to 5. So the point 4, 2 is just 1 unit away from the axis of rotation, which is x is equal to 5. So my other unit, or my other point, is going to be at 6, 2. And then my other point was 1, 1, and that 1, 1 was 4 units away. So 1, 2, 3, 4 units away from my axis of rotation. So that's 1, 2, 3, 4. So at 9, we're also at 1. There we are. Which means at 10, we're right back down at 0. So this square root, when it's reflected across the square root of 5, or sorry, when it's reflected across x is equal to 5, looks like this. There we are. And so again, we're going to get a rotation here. As such, the bottom part down here creates a rotation as well. So we have this bottom part being rotated as well. And we have this inner part that we're also rotating. That inner part is creating this slanted piece there we are. And so again, you can have a slanted piece this way, a slanted piece this way as well. There we are. Perfect. And so what this is creating then is it's creating this volume for this given figure. So what we want to do then is we want to find what is the volume for that figure, and we want to use cylindrical shells. Now, if we're going to use cylindrical shells, then that means that we have to choose our cylindrical shell height to be parallel to the axis of rotation. That means my cylindrical height, and again, the cylindrical height is only going to be measured for that area. So this is my cylindrical height. That's going to be h. All right, so when I go through and I find that, I'm going to find that h value wherever that may be. And let's say that my h value is here. Here we are. So there's my h value. Now I'm going to rotate this about x is equal to 5. Meaning that we're now creating a circle that has a radius, or that has an embedded center at x is equal to 5. So that radius that we are looking for is going to be the radius, let's see if I can grab this here, that's going to be the radius made by the axis of rotation over to that sample point that we're choosing. For this height, we're going to have a sample point of x, because it's going to be on the x values. Therefore, when we want to find the radius, we need to find the distance between x and x is equal to 5. Well, how do we find that distance? Anytime that we want distance, and this is a one-dimensional distance, is we do right minus left or top minus bottom. So we do right minus left, so x is equal to 5 minus x. So the radius then becomes 5 minus x. And again, that radius is being measured from here, right minus left. We do some x value, therefore the radius becomes 5 minus x. Cylindrical shell is then created here. There we are. And the height. Well, the height for the cylindrical shell, it's determined by the two functions. Therefore, the height for that cylindrical shell is going to be the top function minus the bottom function. But since we're going to be integrating with respect to the sample point that we're in, which is the x values, I need my whole functions in terms of x. Which means I need to do top minus bottom, so the square root of x minus y is equal to x over 2. So that's minus x over 2. And let's condense this just a little bit more. That's my x value. There we are. So as I'm finding this volume for this figure, we know that we're integrating from 0 all the way to 4, because our sample point, meaning our radius that we're finding, is going to be in the x values, and that radius is 5 minus x. So here's your circumference, 2 pi times r, where r is this radius that we found, which is 5 minus x. Now we need to multiply by the height. The height in this particular instance is going to be top minus bottom for these functions top is the green function, so that's square root of x, minus the bottom function, x is equal to 2y, but we need to solve this for y, which means y is equal to x over 2. So therefore, my function is the function where I have the square root of x minus x over 2. I need the thickness for the shells, and that's going to be dx. So these circular shells, or these cylindrical shells now, are then being integrated from 0 to 4, and we're about to find out what they're going to be. So again, 2 pi, that's a constant. We integrate from 0 to 4. This is going to be 5 minus x multiplied by x to the power of 1/2 minus, let's say, 1/2 x dx. Now, in order to solve this, we need to distribute, because we can't solve it directly. We can't do a u substitution or anything. So let's go ahead and distribute. 5 times x to the power of 1/2 becomes 5x to the power of 1/2. 5 times negative half x, that becomes minus 5/2 x. Negative x times x to the power of 1/2, that becomes negative x to the power of 3/2. Negative x times negative 1/2, that becomes positive 1/2 x to the power of 2 dx. Now we integrate. So I'm going to integrate my first term, add 1 to the exponent. That's going to be x to the power of 3/2. Multiply by the reciprocal. So I'm going to multiply by 2/3. So 2/3 multiplied by 5. That's 2 times 5 divided by 3. So that should be 10/3. There we are. Minus, add 1 to the exponent. That x to the power of 2. Divide by that power. So 5/2 divided by 2 will now get us 5/4. Minus x to the power of, add 1, that's 5/2, multiplied by the reciprocal, that's 2/5, plus x to the power of 3 multiplied by the reciprocal, and that will now be 1/6. And this is evaluated from 0 to 4. So evaluating this function, now every single term is a monomial, and they all contain a variable of x. So if I insert the value of 0 into each term that's a monomial, everything's going to cancel. So I'm only going to evaluate this function at 4. So I'm going to have 10/3 times 4 to the power of 3/2 minus 5/4 times 4 to the power of 2 minus 2/5 multiplied by 4 to the power of 5/2 plus 1/6 multiplied by 4 to the power of 3. This is then 2 pi. So 4 to the power of 3/2. I'm going to do the square root first. Square root of 4, that's going to be 2. So 2 to the power of 3, that's 8. 8 times 10, that's going to be 80. So that's 80 divided by 3. 4 squared divided by one of the 4's, that's just going to be 4 times 5. So that's going to get us negative 20. Once again, 4. Square root of that, that's 2. 2 to the power of 5, that's 32. 32 times 2, that's going to be 64 over 5. Plus 4 to the power of 3 is going to get us 64, but then 64 does get divided by 6 quite nicely, and we get 32 over 3. So I have all these fractions. They're all going to have a denominator of 15. So let's make sure we get a denominator of 15 going. So 80 divided by 3 minus 20 minus 64 divided by 3 plus 32 divided by 3. This should get us an answer that my calculator is telling me is negative 4, but I don't think that's my answer here. Plus 32, did I do 32 over 3? And I believe I did. Yeah, 32 over 3. So what did I do incorrectly? Let me double check, everybody. All right, so I'm not quite sure what was happening, but apparently I did nothing wrong. I just input this into my calculator incorrectly. So we get 2 pi multiplied by the quantity of 68 over 15. And when we multiply 68 by 2, so when we multiply 68 by 2, we should get 136. So this should be 136 pi divided by 15. And again, this is going to be some cubic units because we're finding a volume. So when you're trying to do these rotations, you always want to focus on what is your method. Are you going to use cylindrical shells, or are you going to use the cross-sectional method? And remember, the cross-sectional method involves the cross-sections being perpendicular to the axis of rotation, whereas the cylindrical shell method focuses on the cylindrical shells being parallel to the axis of rotation. So please make sure that you are aware of that. All right, and both of these methods are interchangeable. We can definitely solve, or we can definitely find volumes of these solids by using either method. All right, we just have to get creative with them. So I hope that you all enjoyed this lesson, and I look forward to the next one where we're going to be talking about work. Till then, stay safe.